Hey everyone, so today we have a fun probability question involving dice again. So the question is, Bob will roll a fair six-sided die until he gets a 3. What is the expected value of the highest number he rolls throughout this process? Okay, so let's look at some toy examples to build our intuition. So say Bob rolls a 1, a 6, a 4, another 6, and then he rolls a 3. We stop at 3. Okay, well clearly the highest value is 6 in this case. Let's look at another example. Bob rolls a 1, a 2, a 2, and then rolls a 3. Well, now the highest value is 3. So just off of these examples, we can see that it's impossible for 1 or 2 to be the highest number in the sequence because we're always going to end with a 3. We don't stop before that. Let's write out this a little bit more mathematically. Let x be the random variable, indicating the highest value in the sequence of dice rolls. Okay, so just off our examples, we can clearly see that probability of x being 1 and the probability of x being 2 is 0, right? So now let's go to our expected value formula. The expected value of x, right, this is what we want to solve in our problem. That's simply the sum of all the probabilities times the value itself. Okay, well we already solved for x equals 1 and x equals 2, so now we just need to figure out what the rest of the probabilities are. Okay, so what's the probability that x equals 3? Well, let's think about this intuitively. The only way I can have x being 3 is if none of the 4, 5, or 6 rolls before 3. I don't care about what happens with the 1s or the 2s, right? We're always going to end on a 3, so if I just happen to roll a fat string of 1s and 2s, then my probability, then I always have 3 as my answer. So because we don't care about repeats, we only care about the sequence of unique values, right? So let's consider only the sequence 3, 4, 5, and 6. Well, there are 4 factorial ways to arrange this sequence. And if we stick 3 at the beginning, then there are 3 factorial ways to arrange 4, 5, and 6. So just from a combinatorics argument, we can say the probability of x being 3 is 3 factorial over 4 factorial, which is simply 1 over 4th. But a slightly more clever way to think about this is you can think of these as slots, right? So 3 is in slot 1, 4 is in slot 2, 5 is in slot 3, and 6 is in slot 4. Well, the only way I can have 3 being the max is if 3 goes in slot 1. By symmetry, 3, 4, 5, and 6 each have the same chance of being in that first slot. So since there are 4 numbers, then 3 has a 1/4 chance of being in that first slot, which agrees with our combinatorics approach. Okay, let's now consider probability of x being 6. Using that previous argument, we can do the same thing, right? How can 6 be the largest number? Well, it has to come before 3. I don't care about any of the other numbers. So if we only consider the sequences of 3 and 6, right? Each number has a 1/2 chance of being in front of the other, being in that first slot. So that means the probability of x equaling 6 is 1/2. Okay, cool. Let's now consider probability of x being 4. How can that happen? Well, clearly I don't want 5 or 6 to come before the 4. But I also need to remember the constraint that 4 needs to come before 3. In other words, I need to consider sequences starting 4, 3, and then I can fill in the rest after, right? We can put in 5 or 6. Well, how many ways are there to do that? 2 factorial ways. which is just 2. Therefore, out of 4 factorial ways to do this, we have 2 factorial arrangements. And what is that? That is just 1/12. Nice. Okay, well, we've done x equals 3, x equals 6, x equals 4. Let's do probability of x equals 5. How can that happen? Well, first of all, I clearly need a 5 to come before the 3. 5 needs to come before the 3. And I also need 6 to come at the end, right? This means I only need to consider where the 4 is going, right? The 4 can go here, the 4 can go here, and the 4 can go here, or the 4 can go at the end. So how many ways is that? That is simply 4 ways. Oops, not 4 factorial ways, that's just 4 ways. So we have 4 over 4 factorial, which is simply 1 over 6. Okay, cool. And just to double check that everything checks out, let's add everything together. So 1/4 plus 1/2 plus 1/12 plus 1/6. If I put everything over a common denominator of 24, then I get 6 plus 12 plus 2 plus 4, and I believe that equals 24. So that means we did our math correctly. Okay, well, all that's left is we need to plug in our values into the expected value formula. So expected value of x is simply, let's see, probability of x equals 3, so we have 1/4 times 3 plus, okay, let's look at x equals 4, 1/12 times 4, and then 1/5, so we have 5 times 1/6. And finally, x equals 6, we have 1/2, so that's 6 times 1/2. Now let's simplify everything. So how about we put everything over a common denominator of 24. So 3/4 becomes 18 over 24 plus 8 over 24. Sorry, my handwriting's a little bit ugly. Plus 20 over 24 plus 72 over 24. And this becomes, okay, 72 plus 18, that is 90. 90 plus 28 is 118 over 24, which equals 59 over 12. So this is the expected value of the highest number. And if we now plug this into a calculator, we can see that this is about 4.92. So thank you everyone for watching. This problem is relatively straightforward, but we did need to come up with the idea of only considering the unique numbers. And in problems like this, sometimes it is really useful to, ignore all of the red herrings and only consider what is important, because that simplifies the problem significantly.